Okay, so we wanted to finish up our discussion of the model of the atom. So from Bohr, we have some additional changes that were made to the model from Schrodinger. And so remember, basically all of our evidence at this point is based on these emission spectra that are kind of changing what we know about electrons. And so according to Rutherford, the electron would be at any distance from the nucleus. And if that was the case, basically we would have more of kind of a ramp-like structure. Our electron could be anywhere in terms of energy. And we would see a full spectrum of light being emitted by atoms, but we don't. And so we know that that Rutherford model can't be correct because we don't see that. We instead see that emission spectra like we had talked about. And so remember, emission spectra are giving us just those single lines of light of different colors based on the energy of the transition that our electron is making. And so if our electron makes, basically a small transition in energy, we get a smaller energy wavelength of light, like red light, for example. If we have a little bit higher energy transition, a bigger jump, then we're going to get that blue light, for example, with hydrogen or kind of cyan. And then even higher energy, we would get a higher energy light like violet. And so again, notice that in this picture, they are more like stair steps. They are going to be standing on the step. That electron can be at that step of the energy, but it cannot be in between. And so that's why we're not getting every color being emitted here, because we are really only getting our electrons being at those very specific energies. And so Bohr's model of the atom, again, has these orbits that the electrons are following. And as the electrons get further from the nucleus, we have those electrons really having more energy as they go out, transition out by absorbing energy. Again, they're going to have more energy in those spaces. As they fall back in to energy levels that are closer to the nucleus, those electrons will then emit that energy. The problem is, and this is good and bad, but this was really great evidence that was supported by that emission spectrum of hydrogen. His understanding and calculations relating to that really were supportive of the hydrogen atom. Again, he was saying that those electrons were moving around the nucleus in these specific orbits. And both him and Schrodinger said, those electrons cannot be in between those orbits, really. Okay. But Schrodinger's model was not quite so perfect. It was not saying that those electrons were exactly following that path every single time. It was a little messier. And he described it more as an electron cloud, or the probability or the highest probability of where an electron will be found. So his is a probability density. Notice that we have all those dots there. The more dots we have in a spot, the more probable it is that we might find an electron in that area. His evidence was that this worked, his model worked better for more complex atoms, meaning all the other atoms that are out there, which have more than one electron. Hydrogen that Bohr used to support his idea is really the most simple atom that we have. It has one electron, mostly one proton. Many of the hydrogen atoms don't even have a neutron. And so it's really kind of only one case where that worked. But Schrodinger's model works better as we get to more and more complex atoms with more electrons. He also has evidence with mathematical modeling. And so this is where we use a lot of calculus in chemistry. But if we want to describe those probabilities of where an electron is going to be, we're going to have to use some mathematics to help us with that. So these energy levels are really, what we are talking about now with our modern model of the atom. So according to our modern model, electrons are going to exist only at these fixed energies or very specific energies. The modern model describes a region in space in which the electron is likely to be found. It's really that probability or electron cloud. And instead of calling it an orbit, we now call it an orbital. That little difference in the word makes a big difference, actually. And so Instead of it being this exact path that it's going to follow, it's a probability of where we're most likely to find the electrons. The location of each electron can be described in terms of the probable distance from the nucleus, or the energy level, and we abbreviate that with the letter N. And so we actually see that this connects with the periodic table. Although we didn't necessarily know that when the periodic table was first being developed, we have since figured that out, that there are all of these connections between electrons and the organization of the periodic table. And so if we are thinking about our periodic table, it can tell us the number of energy levels needed for the electrons in an atom. We can't fit them all into one, depending on how many we have. And so it's the rows, those horizontal rows on the periodic table that we're going to look at. Those are called periods. I always think about this like if I'm writing a sentence, I write it horizontally across and I put a period at the end. So periods on the periodic table must go horizontally across, and we could put a period at the end. So periods are horizontal, and the periods are then numbered 1 through 7. The row that starts with hydrogen is actually called period 1. The row that starts with lithium is period 2, and it's that period number then that tells us the number of energy levels of electrons an atom has. Basically, how many layers of electrons do we have for a particular atom? So if we look at our periodic table, we can actually do some labeling here. So like we said before, hydrogen would be period 1. Okay, so everything in period 1, which it's not always expected, but some people kind of lose it on their way across, but hydrogen and helium over here are considered both period 1. Okay, hydrogen is up here because it's a little bit unique on the periodic table, so we'll get into that soon, but it is period 1. Our next period then is period 2. So everything that is in this row going across would have 2 energy levels of electrons, or in other words, they would have like 2 layers, 2 shells of electrons. And sometimes chemists do just refer to them as shells. The next would be period 3. And that, again, it continues as we go over here. We're going to follow it in order of atomic number. So that number at the top of our periodic table square. Then we have period 4, period 5, period 6, and period 7 finally. One thing to note is that these 2 rows down here at the bottom, they would actually fit in here in period 6 and period 7. Again, notice our atomic numbers, 55, 56. We're going to follow them in order, so that we would come down here, go 57 through 70, and then we would come back up here. Okay, and so this is a little bit unique because of really kind of when those elements were discovered, and there was a little rearrangement that has occurred here. But also by putting them down below, it saves us. If we had to squeeze them in there, either they would have to be really small for our periodic table to fit on the page, or we'd have to have a much longer page all the time, and so that's just not super convenient. So let's talk more about the periodic table. So again, electrons play a really big part in determining the chemical and physical properties of an element, okay? And so electrons are really like the bumpers on an atom, okay? So just like the bumpers on our car, when 2 cars hit, usually it's the bumpers that are hitting first, okay? It's not like the cup holder in the center console that's hitting first, it's the outside of the car. Same thing with our atoms. Those electrons are on the outside, and so when 2 atoms hit, it's the electrons that are going to interact, and that's determining really what's happening in chemical reactions. We can generally categorize our elements like they have done in the past, and historically they came up with 3 major categories. There were metalloids, which kind of have properties in between metals and nonmetals. They are semiconductive, meaning they're sort of conductors. Silicon is in here, which we use for semiconducting computer chips and things like that. But we also have metals then. Metals are going to be shiny. They're ductile, meaning I can draw them out, pull them into a wire. They are malleable, and they're good conductors of heat and electricity. And so that's why I use them in wiring. I use them for my pans in the kitchen and things like that, because they're good conductors. And then we also have our nonmetals, and nonmetals are dull and brittle and not conductive. And those are things that many times are also even just a gas, okay? So we have those kind of three major categories that were originally determined by people. People like to kind of categorize and group things, and they look for similarities and differences to be able to do that. So these were three major categories that scientists came up with long ago. But over time, the periodic table developed more, and it took time for it to develop into what we see today. And so again, here you can kind of see there are a bunch of these here in the middle. They are shiny. Mostly metals are grayish, with copper and gold being kind of exceptions to that. Many over here you can see are gases, or have are very colorful, and that's something that's generally pretty characteristic for nonmetals. And there are a bunch down here at the bottom where it's just got people there. It's not because those people are made out of elements, but it's because those are the people who maybe the element was named after. They may have been the person who discovered it, but they may not have been. And many of those, we don't have any sort of picture because of the fact that they are radioactive elements, and so they just do not last very long. They have pretty short lifetimes. So how did the periodic table develop? So the periodic table actually was first developed, or who's considered the father of the periodic table, is Dmitry Mendeleev. And Mendeleev certainly was not the only person that contributed to this. There were other people along the way, but he really made some huge changes in the periodic table and what we could do with it. And so he listed elements by increasing atomic mass. He noticed that there were these regular or periodic patterns for the physical and chemical properties. And so again, when we say that it's periodic, we mean like just like a week, every week we come back and have another Monday. That's a periodic change that is happening. We have periodic changes in our elements, and we see that they go through this pattern and then they repeat. And the thing that made Mendeleev's work really different is that he was able to accurately predict the properties of elements that had not yet been discovered. And that was really different. People hadn't been able to do that as accurately as he was up until this point. And so, for example, one of the elements that Mendeleev predicted was actually the element germanium. And so what Mendeleev predicted is that he called it eka-silicon because it would have been right below silicon on the periodic table. And he said, I think it's going to have an atomic mass of 72, a density of 5.5. It's going to be kind of a dirty gray. It's going to have some densities and boiling points and things like that for some other compounds, such as what are shown here in this table. Well, in 1886, when germanium was actually discovered, his his predictions were very close to the observations, the observed properties of that element, actually. And so, again, he was able to predict this, and then they were able to discover it, and it supported what he had come up with. Now, Henry Moseley was another scientist who you may not hear as much about, but he actually made huge contributions to the organization of the periodic table. And there is a little video clip that is attached in the speaker notes if you want to take a look at that. Henry Moseley's story is actually super interesting. And if you notice here the dates, he did not live very long. He was a really amazing scientist. He made again, some really amazing discoveries in his short lifetime. But unfortunately, he was also had to go into the armed forces when the British were in World War I, and unfortunately, he was killed there. And so it was really after that the British government looked differently at having scientists go into war zones and having to be in combat, and they kind of changed the roles of scientists who were in the Army. So if you want to learn more about that, you can click on either of the links that are included so you can learn a little bit more about him. It's a pretty interesting story. So what Moseley did that was really different is he determined that the nuclear charge or the atomic number for elements, really that number of protons, was the key thing that needed to be used to put our elements in order. And so again, he was the one who figured out that nuclear charge. He rearranged the elements in order of atomic number. It wasn't that different than the way that Mendeleev had done it, but there were a few things that moved. And if you look at your periodic table, you'll see that things don't go perfectly in order of mass. If you go from like iron to cobalt to nickel, that is going to, you'll see the mass kind of go up and then go down again. But that is how it fit best when we actually looked at rearranging things by atomic number or number of protons. This is our current arrangement of the periodic table. We found that things fit best with those periodic properties when they are arranged by atomic number. So again, Moseley left a lasting impact on the arrangement of our periodic table. So last thing here, we generally, again, talk about things arranged on the periodic table based on, are they in the same column or are they in the same row? But in science and in chemistry, we don't talk about them as columns and rows. We talk about them as periods and groups. And so periods, again, are those horizontal rows going across, and those are going to be things that have the same number of energy levels of electrons. Groups, or sometimes families, are those vertical columns. They are going up and down. I think about it kind of like a family tree is going up and down, okay? And again, families or groups are going to have much more similar properties to each other, just like you and your family probably have some similarities, more so than things that are going across the period. Just because things have the same number of energy levels of electrons doesn't mean that they act the same. And so as we continue on, we'll see a little bit more about that and learn more about our different groups in our next discussion.